Okay, so hello, my name is Macau, and today we're going to be doing the 1999 Step 2 Question 3 on the pure section of the paper. So we're given this function Sn of x, where we want to calculate the nth derivative of e to the negative x cubed, all multiplied by e to the x cubed. So first we're going to want to calculate S2 of x, which would be the second derivative of e to the negative x cubed. So we can calculate the first derivative as using chain rule, so minus 3x squared multiplied by e to the negative x cubed. Therefore, the second derivative of that, we can use a product rule here, so u equals minus 3x squared, u prime would be negative 6x, and then our v would be e to the negative x cubed, and then our v prime would be minus 3x squared, e to the negative x cubed. Okay, so this derivative would be u prime v, so minus 6x, minus 6x e to the negative x cubed plus v prime u, negative 3x squared, e to the negative x cubed, and then minus 3x squared again, so I'm just going to square that bracket there. Squared. Okay, so our S2 of x, S2 of x is going to be e to the x cubed, all multiplied by minus 6x, and I'm going to change this e to the negative x cubed here into 1 over e to the x cubed, so it's a bit more clear what we're about to do. And then minus 3x squared would be 9x to the 4, and then again 1 over e to the x cubed. So you can see when we distribute this over the addition, this and this are going to cancel out, and then also this and this are going to cancel out, which means that S2 of x is going to be 9x to the 4 minus 6x as required here. Okay, so now we want to calculate S3 of x. So I'm just I'll just move to the side here. So S3 of x is going to be e to the x cubed multiplied by the third derivative of e to the negative x cubed. And well, we already know our second derivative is this, so we want to calculate the derivative of minus 6x multiplied by e to the negative x cubed plus 9x to the 4 multiplied by e to the negative x cubed. So what we can do to make this a little easier, we can pull out a factor of e to the negative x cubed, which will just leave us with, in this bracket, 9x to the 4 minus 6x. Then we use a product rule again, so we'll say u equals e to the negative x cubed. U prime would be minus 3x squared, e to the negative x cubed, and then our v would be 9x to the 4 minus 6x, and v prime would be 36x to the 3 minus 6. Have I got that right? Yes. Okay. Therefore, our third derivative of e to the negative x cubed, u prime v again, minus 3x squared, e to the negative x cubed, 9x to the 4 minus 6x, plus v prime u, so 36x to the 3 minus 6, u is e to the negative x cubed. There you go. Okay, and so S3 of x would be e to the x cubed multiplied by minus 3x squared 1 over e to the x cubed. Oop, this doesn't really look like a power here. Make sure your working is clear when you're showing your powers. All multiplied by 9x to the 4 minus 6x plus 36x cubed minus 6 1 over e to the x cubed. So when we distribute this power again, we get an s3 of x equals, distribute this exponential, we get in the brackets minus 3x squared times 9x to the 4 minus 6x x plus 36x to the 3 minus 6. If we just simplify that a little bit, we get minus 3x squared times 9x to the 4 would be minus 27x to the 6. Minus 3x squared times minus 6x would be plus 18x cubed. Then we have a plus 36x cubed minus 6. Therefore, S3 of x equals minus 27x to the 6 plus this is an 18. 18 plus 36 is 54x cubed minus 6. Okay, cool. Now, the question states we want to prove by induction on n, so on n, that Sn is always a polynomial. Okay, cool. So, I'm going to move to the left here. You know what? I'll bring the question with me. How do I? Oh, it's not. Wait, let me select it. There we go. Okay. So, the way induction works is we are going to, well, we've proven the base case here, so we don't actually need to prove a base case again, but usually we'd prove the base case, which is, you know, like a low number for n, so let's say 1 or 2, 2 works. Base case S2 of x is a polynomial. Which we showed was 9x to the 4 minus 6x, so that's true. Okay, and now we are going to assume, assume for induction that, now we're going to assume that the kth case is true. So sk of x equals e to the x cubed times, multiplied by the kth derivative of e to the negative x cubed is always a polynomial for k, or positive integers k, because I mean that's what derivatives are. We can't calculate any half derivatives here, so yeah. Now for our inductive step, we want to prove that the k plus 1th case is true. And so our goal essentially is to get to sk plus 1 of x, which would be the k plus 1th derivative of e to the negative x cubed. Okay, so what we can notice that if we start from this here, well, our sk plus 1, by proving that this case is true, sorry, I just want to clarify. Proving this case is true means that we prove that this is a polynomial. So our goal, polynomial, our goal is to prove that the k plus 1th case is a polynomial. So what we can do is we can notice that this k plus 1th derivative is just the derivative of the kth derivative. Because with this induction, or these inductive proofs, you notice that you always want to kind of force your assumption to pop up. And so by doing this, we've kind of forced this kth derivative part to come up. And so what we can do is we can say, well, s of k divided by e to the x cubed equals the kth derivative of e to the negative x cubed. And that's just come from our assumption here, this formula that we have up here. That's what this is. And so if we plug this directly into k plus 1, we say s k plus 1 of x would be e to the x cubed times the derivative of this expression here, which is sk of x. Now this over e to the x cubed, I'm going to just make this into e to the negative x cubed because I like to work with product rule instead of quotient rule here. So yeah, now product rule again, u equals sk of x. U prime, well, we don't really know what the derivative is, so I'm just going to say it's going to be s prime k of x. V would be e to the negative x cubed, and then our v prime is going to be minus 3x squared e to the negative x cubed. Okay, sorry, this is not really that clear. E to the negative x cubed. Okay, therefore our sk plus 1 of x is going to be e to the x cubed, and the derivative would be s prime k of x multiplied, well, u prime v, so e to the negative x cubed, plus, and then v prime u minus 3x squared e to the negative x cubed. U is sk of x. Oh, yep. And so multiplying by our this e to the x cubed again. You can see our previous steps are kind of popping up now. We just get s prime k of x plus minus 3x squared times sk of x. Now, if this isn't clear, what we've just shown essentially is that, well, we've assumed already that sk of x is a polynomial, right? And therefore, the derivative here, derivative of a polynomial is a polynomial. Sorry, I spelled that wrong. Polynomial. And also this is a polynomial too. And multiplying a polynomial by another polynomial term is still a polynomial. Hence, is also, oh sorry, not also, it just is a polynomial. In these kinds of questions, you'd want to write out that you want to show your examiner that you know that this is definitely a polynomial by writing everything out here, as in explaining why it's a polynomial specifically. And so hence sk of 1 of x is a polynomial. Okay, therefore, now this is our conclusion here for our induction. Therefore, we have shown that, excuse my handwriting, that if the nth, if the kth case is true, then the k plus 1th case is also true. And since we have shown true for k equals 2, as in our base case S2 of x, we have proved that Sn of x, which is e to the x cubed times the nth derivative of e to the negative x cubed, is always a polynomial for n in the set of our positive integers here. There we go. That's our induction done. And that's kind of the main part of the step question done. Okay, cool. Last bit. I'm going to again bring the question over here. So, we want to show that if the derivative of our function s of n equals 0 for some value of a, then Sn of a times Sn plus 1 of a is less than or equal to 0. Okay, so here, dsn over dx. Well, that is just the same as that, right? I remember we already defined that s prime of n here, or s prime of k, is the same arbitrary variable. And we said, well, here, s prime of k, we can rearrange this formula for s prime of k. So we can say s prime of k equals sk plus 1 of x minus 3x squared sk of x. Wait, hold on, I think I missed a part. Oh yeah, sorry. Make sure you read the question. We need to determine the order of the polynomial and the coefficient of the highest power of x. Okay, hold on, let's do that first. Oops. Let's delete that. Okay, cool, sorry, I forgot about that bit. So, well, we know that if we go back to here, I'm just gonna rub this out. So, I'm going to rewrite this equation over here real quick. So, sk plus 1, sk plus 1 of x equals the derivative plus, I think it was it minus? Minus 3x squared sk of x, okay. Yep, minus 3x squared sk of x. Okay, well, we know that the order of this so yeah, the order of sk plus 1, right, is always going to be 2 above the order of s of k. And the reason for this is because, well, we know the order of s prime is going to be exactly 1 less than the order of s of k, because, I mean, when we differentiate, we remove 1 off the power. Therefore, this s prime won't really matter in terms of determining the highest order. What matters is the order of sk of x. Multiplying it by 3x squared means we add 2 to the highest polynomial term in sk of x. Therefore, the order of sk plus 1 of x is going to be exactly 2 higher than the order of sk of x every time. So I'm just going to write that down. The order of sk plus 1 of x is always 2 above the order of sk of x. therefore, if the order of S2 of x equals 4, we showed here 9x to the 4 right at the start, and S3 of x was 6, well, S4 of x must be 2 more than that. And so we can see this relationship where this 2 becomes a 4, this 3 becomes a 6, this 4 becomes an 8, implying that our order of Sn of x is 2n. Okay, so that's the order. And now we want to know the coefficient of the highest power of x. Okay, well, we can use the same logic here and say the coefficient of the highest power was always minus 3 times the coefficient of the highest power of Sn of x, right? So I'll write that down. It's this exact same principle as earlier. The coefficient of the highest power of Sn plus 1 of x, or sorry, we'll keep it in terms of k, is always minus 3 times the coefficient of the highest power. I'm just going to write dot the dot of sk of x. Okay, well, we can do the same thing. Well, we know S2 of x, what was the coefficient of the highest power? It was 9. S3 of x was minus 27. So then S4 of x would be what? Minus 27 times minus 3, which would be 81. So you can see, well, pretty quickly, we're multiplying by minus 3 each time, right? Therefore, the coefficient of the highest power is going to be minus 3 to the power of n. If we square minus 3, we get 9. If we times it by, if we cube minus 3, we get minus 27. And you can see we're just multiplying by minus 3 each time. So there we have a 2n and a minus 3 to the power of n. Okay, now we can move on to the derivative part, the last bit. Okay. Cool. So I'm just going to rewrite this same equation we had earlier. I'm going to do it in terms of n now. Okay. Rearranging this for s prime of n, we get s prime of n of x equals Sn plus 1 of x minus, oh sorry, plus 3x squared Sn of x. Okay. And so that is going to be our dsn over dx, remember? And therefore, we can use that and say, well, for some value of alpha, this equals 0, right? So plugging in alpha, S alpha equals 0, implying that Sn plus 1 of alpha equals negative 3x squared Sn of alpha, right? And so, well, if we look at this here, do you see how we're a product of Sn plus 1 of A? Or sorry, it says A, but A and alpha is the same thing. n of a multiplied by Sn plus 1 of a is less than or equal to 0. Well, what we can do is we kind of want to, force this result to come up. And so if we multiply both sides by Sn of alpha, well, what happens here? Let's see. Well, we get this nice result on the left that we wanted before. So we have our Sn of alpha times Sn plus 1 of alpha, right? And on the right hand side, we have this minus 3 x squared times Sn of alpha squared. And well, what we can do now is, if you notice here, right, we have this less than or equal to 0, and here, this is where the step, kind of practice really helps. We have a bunch of squares, and so if we can somehow try write this as a square, then maybe we can force that greater than or equals to 0 result to pop up, because the square number is always greater than or equal to 0. So first, I don't like this negative, so I'm going to multiply by a negative on each side. So I'm going to put a negative there, and then I'm going to remove this negative. And now I'm going to write this as a square, a perfect square. So this would be root 3x Sn of alpha all squared, right? That would be our minus Sn plus 1 alpha Sn of alpha. And so since this equals a square, then we can automatically say, well, it must be greater than 0. Right? Because the square number is always greater than or equal to 0. And what you notice is that because there's a negative there, and we don't want that negative, do we? Multiplying an inequality by a negative number flips the inequality. Therefore, there we go. And that's the end of the question.